So we started recording. So hello everyone and welcome to the fifth of the alumni talk series presented by Aakashganga. We are delighted to have Nandini Hazra from the class of 2019 with us today as a speaker. Nandini is a PhD student at the Gran Sasso Science Institute, Italy. Her area of research is astroparticle physics and multi-wavelength astronomy. She is currently working on surface brightness fluctuations of the galaxies, which is also the topic for today's talk. So without further ado, I would like to hand over the stage to her. Over to you, Nandini.
Thank you so much. Thank you so much for organizing this talk. I will start right away, but before that, I will just say I typically do very, very short talks. And this one is very short. I've tried to make it as less technical as I could. But if at any point you feel like you don't understand what I'm saying, you can stop me. And I like to have long discussions. So if you have questions of any kind, just stop me or save it for the end, whatever you like. So let's start. Okay. Can you see my screen?
Yeah, it's visible.
Okay, good. So I will talk briefly about surface brightness fluctuations, which is a relatively new rung on the distance ladder and is finding a lot of application very recently. So even though this method has been around for nearly 40 years, not a lot of people use it. Not a lot of people know how to use it. It's very, very technical in its nature. And I think you'll appreciate as I talk more and more about it is that there are very, very typical features in it which make it not so accessible as a method of analysis to a lot of people. But nevertheless, it's a very, very accurate method. It provides distances of up to 5% accuracy. And recently, a few groups have been doing a lot of good cosmology with these distances. So I'll talk briefly about this. To just introduce the topic, distances are important in astronomy at all scales. So you start with your parallax distances at very, very short, very, very close to the Earth within the galaxy. And then you move on to the extragalactic distances, which is you take your Cepheids and then you have your RLI calibrations, and then you gradually build upon these calibrations and you go farther and farther. As you go from one distance indicator to another, you also change your accuracies, you change the way you measure. But the important point to remember is that these distance measures build on each other. So when you have a distance indicator which is very, very far from the galaxy, you also rely on the ones that are closer to you to build upon these measures and then go farther and farther. So as you can see, if you can see my cursor, SBF is right about here. It is quite accurate of distances up to 100 megaparsecs. And yeah, that is the typical range within which it's used is between, say, 10 and 100. Typically, you don't go all the way up to 100, you go up to 90 or so, but that's the idea. But what is surface brightness fluctuations? So the basic idea behind this technique is that the closer a galaxy is to you, the more features you can see in it. So you can see this particular galaxy on the right is 100 megaparsecs away. So when you look at the galaxy, you cannot make out individual features in it. So it all looks like one smooth blob or a smooth halo. But if a galaxy is very close to you, for example, this one at 0.75 megaparsecs, you start to see features in it, which is typically because of the stellar population in this galaxy. So the closer a galaxy is to you, the more you can see the individual fluctuations in the brightness that you receive, the luminosity that you receive from this galaxy. And this is something that everyone borrows from this one particular presentation by one of the very, very important people in this field called John Tonry. So what is surface brightness? It's the product of your flux and the density per pixel of the stars. So flux falls off as the square of the distance. whereas the density per pixel increases as the square of the distance. So when you have a product of the two, the surface brightness is constant. And then you can now measure the RMS fluctuations from pixel to pixel, which gives you the variation, which is a measure that you will then use to measure the distance to this galaxy. I will explain more as we go further. This is just because I have to introduce it, so I'm going to tell you what the definition is. So this is the mean luminosity. This is taken to be the ratio of the second moment to the first moment of the luminosity function. So basically, Nj is the number of stars who have luminosity less than Lj. And when you define this particular quantity here, it has then been observed that from there you can then go to the absolute magnitude of the star. And this, along with some certain 0-point calibration, gives you basically the absolute magnitude of the star, which is which defines the intrinsic property of how the star is supposed to look. Star, galaxy, whatever it is, how it's supposed to look. From there, how do we actually measure these fluctuations? What do we do? When you have an image of a galaxy and you want to find the distance to it using SBF, what do you do? So you start out with an optical image of a galaxy. To this, you fit a smooth model. To fit, what you want to do is you want to remove the very, very bright objects from this image so that you are left with the underlying stellar population. So for this, first you subtract out the central bright object in the galaxy. And once you have done this, you now look for the other bright objects that you have in your field, which could be background galaxies, it could be globular clusters, it could be bright stars in the foreground. And then you mask these objects, and then remove these as well. Now, this has to be very carefully done because once you set these thresholds, you want to be removing the bright objects which are occluding your underlying stellar population, but you do not want to remove these red giant branch stars that you have in the underlying stellar population, because this is what is going to give you the surface brightness fluctuations. So the pixel to pixel variation that you will see in the brightness would be due to the intrinsic property of how the stars are distributed in the galaxy itself. So you do not want to remove these very, very bright stars that are in the galaxy itself. You just want to remove the globular clusters, the foreground stars, the contaminants, the galaxies in the background, and so on. Now, once you have done this, the globular clusters and the bright objects are not the only ones which are making your life difficult. You also want to be removing other contaminants. You want to be removing the dust that is there, which will cause absorptions, which will cause all sorts of artifacts in your image. And these extinctions can come from both the internal dust in the galaxy and also from extinction due to the Milky Way dust. So you want to carefully look at these images and then account for the extinction by these particular factors. And once you've corrected for these effects and you've corrected for your telescope artifacts, such as certain pixels may be saturated, certain pixels may be dead, there might be some cosmic ray tracks, and you have to correct for all of this. And once you have done all of this, now you have a clean image of your underlying stellar population in the galaxy, and you can measure your SBF magnitudes. So this part is slightly technical. I'm sorry if you don't understand completely, but feel free to ask questions. Feel free to stop me if you find something very, very complex and you think that you don't understand it at all. Okay. Now that we are ready to measure the SBF, we fully transform the image we have to get the 1D azimuthal average power spectrum. Now, this power spectrum is fitted with the point spread function model of your telescope, along with the mask that you have used to take out your objects, and a certain photometric noise that your telescope itself has. The photometric noise of the telescope itself can be modeled from you do sky background modelings, and then you can find this constant noise. The PSF model is typically taken by measuring within your image. You take a points, you take a star, and from that you get your PSF. When you have all these components, you then fit your power spectrum, and whatever residuals you have from this fitting, you use this to calculate the fluctuations, which gives you your apparent magnitude of the SPF. And I mentioned the absolute magnitude earlier. So that absolute magnitude will be from a set of empirical calibrations. Sorry, it will be from a set of calibrations. And when you combine it with this, when you combine it with this apparent magnitude that you have calculated, you can then find the distance modulus of the galaxy directly. This is a little bit more technical, and if you want, we can discuss this later, but I don't think it would be appropriate right now, but we can discuss this. The calibration I mentioned earlier, how do you get it? So this can either be obtained, it can be obtained in two ways, and one of them is significantly more used and more reliable than the other. You can either get it from empirical calibrations. So you remember I mentioned the lower rungs in the distance ladder. So you can get these 0-point calibrations from your CFIT distance scales, from other ways of calculating distances. The other way to get these calibrations is from a theoretical modeling of the underlying stellar population itself, which gives you a relation between the color and the distance just based on how your stellar population looks. Now, this is a much more work in progress method. It's not very reliable yet. Not a lot of people use it. A lot of people are working on this kind of theoretical modeling, but it relies very, very, very heavily on a very good understanding of the underlying stellar population, which, even though that's not an unreasonable thing to achieve, it has been difficult to get these theoretical calibrations without the help of any empirical distance calibrators. Okay. Taking a step back, what are the assumptions and considerations that go into this method, this kind of analysis? Firstly, is that it's a given that it's a given that you have to understand the stellar populations very, very well, and they have to be very, very well modeled, which means that once you go farther and farther out into the galaxy, you assume that you understand stellar populations close to us, close within our galaxy, and basically that the lower rungs of the distance ladder are reliable methods of the distance indicators. And only once you're convinced that this is something that you can rely on, only then you can go farther and farther and say, okay, given the models we have in the local universe, we can go farther into extragalactic scales and measure these distances. The second problem, second assumption, is that the red giant branch stars are considered as the dominant source of the SBF signal. But this applies to older galaxies, not to younger galaxies where there is a lot of active star formation, where you could have excuse me, stars in different stages of their evolution. You can have core helium burning stars, you can have asymptotic giant branch stars, and all of this could be contributing to your signal. And it's very difficult to model this because, like I said, a deep understanding of the underlying stellar population is very important to understand these fluctuations themselves. So this ties into one of the disadvantages that I'll discuss later. But this is sort of a very, very important limitation that we face while doing this kind of analysis. The third thing, this is sort of like a consideration, as not as much of an assumption, which is that the candidates which we use for measuring the SBF have to be such that the pixel-to-pixel fluctuations within the image are dominated by the stars themselves, by the starlight themselves, by the Poisson statistics, rather than by certain errors from your telescope, from your CCD, from photon statistics and whatnot. So this means that you have to have a certain exposure time such that these CCD artifacts, these errors in your telescope, these background noise, so to speak, averages out. And what you're left with is a dominant Poisson statistics from the galaxy stellar population rather than from these local effects. Okay. Now, what are the advantages? We have so many distance indicators, so why should we use SPF? One of the big reasons is that at these distance scales, what happens is when you use lower rungs of the distance ladder to get to the higher rungs, what you're also doing is you're adding up your errors. So by the time you get to these 10 megaparsec, 20 megaparsec, 50 megaparsec distance scales, you get very, very huge errors on your distances. But on the other hand, SBF can give you distances accurate to up to 5%, which is very, very valuable at these distance scales. And compared to other methods like supernova, it is much more, it has much less bounds on the error. The second thing is that when you use supernovae to calibrate distances, they are one of the most popular methods to calibrate extragalactic distances. You rely essentially on the fact that there is a supernova in every galaxy that you're hoping to measure the distance to, which may not be the case always. On the other hand, this method uses archival data, and what you typically end up doing sometimes in electromagnetic follow-ups of gravitational wave events is that, and we can also discuss this later in detail, is that you take a mosaic of the region of the sky that you have localized your signal to, and then you look at all the candidates that you have from there. You look at your archival data and you try to figure out which galaxy sort of did not have a transient in your archival data, but does have a transient right now. And this is how you sort of localize what galaxy your signal is coming from. And now to measure distances to these galaxies, you're not going to sit and wait for a supernova to happen there. You need the distance right away. So what you're going to do is you can go to your archival data, you can take your optical data from the archives, and you can use it to measure the SBF. And the other advantage, which is the most obvious one, is that you can tie the SBF distances with the other distance indicators and go farther and farther into extragalactic distances. And it's also possible to do very good cosmology. Recently, my group has been doing a lot of work on this. So using SBF distances and supernovae, basically we have taken a huge sample and we've been able to measure the value of the Hubble constant that lies between the supernova estimates and the Planck estimates from the CMB. So this is a huge, the Hubble tension is a huge topic right now in cosmology. And it would be nice if we can use different distance indicators to sort of infer the Hubble constant and then be able to resolve this tension. And also with the advent of third generation gravitational wave detectors, we hope to be closer to a resolution to the Hubble tension itself. Okay. What are the limitations of the method itself? One, as I said, is that the method relies heavily on a basic understanding of the stellar populations. The second thing, which is very, very limiting, is that the fact that you have to mask out so many bright regions to be able to get to the underlying stellar population, and you depend on the population of red giant branch stars, on an understanding of the red giant branch stars to understand this fluctuation and how it gives you an indicator of distance. It also means that certain kinds of galaxies are excluded from this kind of analysis, especially young star-forming galaxies where you have a lot of young stars, where there is a lot of clumping of gas, which causes fluctuations in brightness that do not that do not depend on the underlying stellar population, but on the fact that there are star-forming regions and you cannot get an accurate estimate of the distance from this. So you end up having very, very accurate SBF distances to elliptical galaxies typically, and not to spiral galaxies, for example. So this is a huge limitation. In summary, we can say that SBF is a very reliable distance indicator that fits well within the other distance indicators, and it provides a good intermediate distance indicator that is very, very useful, especially now for electromagnetic follow-ups to gravitational wave events. We have a huge advantage in this respect because we can use archival data in measuring distances to the host galaxies. It has huge applications in cosmology. And the big thing here is that it still relies on the local distance indicators. So there is a push to sort of make it more independent and to be able to infer these distances through the theoretical modeling itself. So that is where I will stop. Thank you very much. And if you're still here, I am happy to take questions.
Thank you, Nandini, for the very informative and well-paced talk. So I would like to encourage everybody to put forward any questions you may have. You can even ask us to read out your questions by typing them in the chat box, or you can unmute and ask for them.
Yeah, so I didn't get quite why are you using the red giant branch stuff?
Okay, so you're using the red giant branch stars because you know that these have moved beyond the how do I put this? So these are the populations that you find in the elliptical galaxies, which are not active star-forming regions. And when you have these red giant branch stars that are not evolving so fast, you're able to then find the pixel-to-pixel variation, which does not depend on star formation. Okay, you can also use this technique itself to determine at what stage of star formation a galaxy is. So the fact that you use red giant branch stars is just to say that the method is more accurate at a certain stage of stellar evolution as compared to others. And this is just it. Is that?
Yeah,
Do you
okay.
understand?
Yeah,
Okay.
and what are the approximate error bars on the distances you all measure?
About 5%.
Oh, okay.
So it's very, very, how do I say this? It's very, very good at these distance scales because typically with supernovae, you have much higher error bounds.
Yeah, thanks.
So it's one of the most, yeah, no problem.
So with the supernova method and other methods, what are the error bars? For comparison?
It depends on a lot of things, but I think about 15% is, yeah, I think about 15, if I'm not wrong, if I'm not mistaken, about 15% is very, very normal, for example. Which is why, so you know that you have the Hubble constant tension from the Planck measurements using CMB and the supernova measurements. And one of the huge reasons why a lot of people prefer the Planck measurement is because you get a lot of systematics from the supernovae. So you have very, very large error bounds on those, and then that ends up giving you a huge deviation. Nobody killed me for saying this, I'm sorry, but yeah, okay.
All right. So could you share your undergrad experience a little and
Absolutely.
Thanks.
So I can see my friend is here, Rajiv. So I started out in 2013. So at first I was a little confused. I didn't know what I was going to do. I knew that I was going to do something with physics, but I didn't know if I wanted to do a bit of biophysics. So explored in the first year, in the summer a little bit. I did a project with Ramana Athreya in Arunachal. I was working on ants with him. I realized during the summer that I was really not cut out for biology or biophysics, but I had a great time working with Ramana, and I think periodically I have gone back to him for advice, and he's always given me great advice. So after that, I was always curious in I wanted to choose between condensed matter, astronomy. Yeah, I think those were my two interests. But then I ruled out condensed matter soon enough because I was pretty bad at that. So then in my second year, after my second year, I did a summer project at the Udaipur Solar Observatory. I did a bit of instrumentation while the telescope was being commissioned. And I realized that I really enjoyed working with data. And then the year after, I went to Germany and I did a project on solar astronomy, but with very, very data intensive. And yeah, after that, I worked briefly with Dr. Nissim Kanikar for one semester, and we were trying to do multi-Gaussian fits to interstellar medium spectra. It was a great experience because it taught me a lot about how to approach a certain problem and how not to do certain things. After that, I think I started my fifth year right away after the eighth semester. I worked with Dr. Dipankar Bhattacharya and Ayuka on X-ray binaries on timing and spectral analysis. Uh, it was a completely new field for me at that point, and it was a steep learning curve, but it was very, very enjoyable. And I worked with some data, read a lot of literature, and yeah, it was a great time. But at the end of my ninth semester, I had a huge mental health crisis. So at that point, I took a lot of time off. And then I came back to my work after almost a 10-month break. And I graduated in December of 2018, one semester after my peers. So that's why I got my degree in 2019. And yeah, it was, if you have any more pointed questions, you can ask me. I don't know how to give a more general summary.
Thanks. I had one more question. So you had to choose between astronomy and condensed matter, and you were confused. You were considering other fields also outside astronomy. But even in astronomy, many freshers who come, like they are fascinated by outer space and astro stuff. But even astronomy is very broad. And how can one go about exploring various subfields in astronomy? And because we have to choose one subfield at some point, like or something like that. So yeah.
So one of the things I was told very, very early on is that I went to Ramana to ask him what I should do, what subfield. I had one of these exact questions. What he essentially told me was, it doesn't matter what you do as long as you do it well. So whatever you're doing, if you put in your entire effort and you genuinely make an effort to understand whatever you're doing, it doesn't matter what you do, and it doesn't matter what you choose. At some point, you might realize that you don't like what you do, at which point you can change. But really, I don't think you should be very, very stressed about choosing a sub-field or even choosing astronomy, because my advisor here, she started out with radio astronomy. She did X-ray astronomy for her master's thesis. Then she did radio astronomy for her PhD. And now she works in 5 different fields, and really it makes no difference because she's motivated, she understands the basics, and she's ready to put in the work to go into a new field. So as long as you're ready to put in the work to go into a new subfield, it doesn't matter what you choose starting out, because it just depends on how much effort you're ready to put in to understand something. So that's what I would say. So if you look at something, it looks interesting, start doing it, follow it through to the end, which is something I struggled with a lot. I did not follow a lot of things through to the end, which was important. It's important to do that. So what you need to have is a holistic understanding of whatever you do, which you get when you follow things through to the end. So instead of exploring 50 different things, you choose 2 things and you do them well, and that's it. Which does not mean that you don't explore, you explore, of course. But you don't need to limit yourself.
Okay, thanks.
I had a general question.
Yes.
How do you account for gravitational lensing while imaging for galaxies?
This is a. You typically account for this while you're creating the pipeline for the galaxy. So when you have a very, very lensed object, I don't think it's a problem for our analysis because you already take care of this in your pipeline, and for our purpose, gravitational lensing is not a problem in this analysis because you take care of this while you're creating the pipeline, and the sources we choose are far away from lensing artifacts. Actually, I don't know if that was your question.
Yeah, okay, thanks.
Yeah. Okay.
So I had a question regarding distance measurement as in general. So as I understand it, the use of supernova as standard candles depends on the assumption that we actually know the theory behind supernova. Are there any theoretical limitations to SBF as well?
Yeah, that you don't understand the stellar populations at all,
Okay.
and that your stars are just completely something else distributed in a different way, and what you look at, which is very, very unlikely. It's much more unlikely than your understanding of supernova themselves. Supernova are quite well understood, even though this is an assumption that we say is behind all these measurements. You do understand supernova quite well, and you understand cell populations even better. So this is the very basic limitation. So theoretically, this is the most important assumption. The second thing is that you don't understand safe fields. So whatever distance calibrators you're using to go from a lower rung to a higher rung are all wrong, which again is very, very unlikely.
Okay, thanks. Also, could you comment on what the problem with CFIDs actually is? Theoretical problem with it?
There is no problem.
No, you said right that we
No,
don't
no.
really understand.
If we don't understand safe fields.
Okay, sure. Okay, thanks.
Yeah, I'm still pretty confused as to how are you all measuring the distances using SPF? I didn't really understand it properly. Like, could you briefly? I mean,
Okay, this is very technical, and to be really honest, I don't think I understand it very well either because I'm very new to this. But I had a lot of difficulty wrapping my head around this as well. So, okay, the very basic relation that you rely on, I was trying to connect my iPad so that I could draw and show you, is that the difference between your apparent and absolute magnitude, if you correct for galactic extinctions, is supposed to give you the distance modulus. Okay, so your the difference between the apparent and the absolute magnitude, subtract the galactic extinction, is supposed to give you the logarithm of the distance divided by 10 megaparsec multiplied by 5, and then you subtract 5. So this is a very well tested, well understood relation. Is that the idea behind this is there is a galaxy at a certain distance d, which is emitting light, and you observe a certain magnitude from it. Now, the difference between the observed magnitude, which is again a way of saying the luminosity of the object, the difference between the luminosity you observe and the luminosity that's emitted by the object itself, This difference gives you how far it is. So this is the underlying idea.
Right, but
How you get there is you have the apparent magnitude of the fluctuations that I told you how to measure in a very convoluted way from the power spectrum. Do you remember?
right. I meant, how do you know the actual luminosity of the galaxy?
This is what I meant by an understanding of the stellar population. This calibration you get from from the exact position of a particular star in your color luminosity diagram, color temperature, your MK diagram basically. Based on where the star is in your MK diagram, you can infer the absolute magnitude. To this, you have to add a certain 0-point calibration, which you get from your empirical distance measures like the Cepheids. Do you understand?
Yeah.
Yeah. And this is what you compare to the observed magnitude that you have from your fluctuations in the past. This is very, very technical, and I don't expect you to understand it right away. So you can send me an email and we can discuss more, but this is basically the idea. So based on where the star is in the MK diagram, you know what sort of absolute magnitude, what sort of absolute properties, luminosities it has, what kind of fuel it's burning, what is its mass. Okay, you know the diagram.
What did you mean by MKL?
The diagram of stellar evolution, basically. At which stage of stellar evolution a star is.
Not the HR diagram, right?
Similar to the HR diagram.
Okay.
The MK diagram is the HR diagram, I think.
Yeah, they're the same. They're the same. Just I think
the axes are different.
It's magnitude axes are different. You got color versus temperature, or color versus magnitude versus temperature.
Oh, okay.
So
Yeah.
it's the 1:1 relation, but different.
Yeah.
Cool. Yeah.
So based on what stage of stellar evolution your star is in, you can understand your what kind of fuel it's burning, what is its absolute luminosity, hence the absolute magnitude, and then the 0-point calibration from your existing distance calibrations.
Yeah, thanks.
And then you can get the galactic extinction from your sight lines, and then you put all of them together and you get the distance.
As a follow-up to his question, is the luminosity like averaged out over all bands?
No,
Like, is
no.
it,
You
or
get
are we measuring it in a particular band?
very, very specific bands. So you
Okay,
have
right.
your SDSS bands. You have, so they are measured in very, very specific bands of the optical wavelengths. So you have your Q band, you have your B band, V band, I band, magnitude, and what I told you was a very, very simplified version of the analysis. You also use the differences of color between differences of magnitude between these bands to also calibrate your distances. So it's you measure these in different bands and then you cross correlate them, and no, they are very, very band specific. Yeah.
Yeah, okay, fine.
Nandini,
Yes.
did you try this method in the LIGO runs for the GCNs, or like whatever the archival data this time?
No. So we are going to try it with O4.
Okay.
And the idea is that once LSST becomes operational, there'll be much more data. Right now, there are pipelines for HSC, the Subaru data.
Okay.
We are developing the pipeline for the Subaru data. There is a pipeline for Hubble Space Telescope. But I mean, we were supposed to do it with O3, but I think that didn't work out. So for O4, there is these two groups in Europe called Engrave and Gravita.
Yeah.
Yeah, the Italian groups. So we will be in both of them, and we will sort of be the contact people in case of a BNS merger with EM counterpart. We will be the contact people for the distance measurement during O4. And then you hope to also do this for Einstein telescope and then LISA and whatnot.
But so what data do you use now? Or
Right
is it what?
Right now, I'm using Subaru data, optical.
Okay.
But then I will do some training on Hubble Space Telescope data.
Okay, okay. But these pipelines are like centralized now, or what is it like?
No, Sujay, it's very so okay. Another big problem that we have is maybe the LSST and HSC pipelines are washing out the SBF signal. So
Okay,
then it's very non-standard. So whatever we develop for HSC, we hope that we'll be able to adapt it to LSST.
okay.
But yeah, and maybe automate it. So then if you automate it, there is some level of independence, but
Yeah.
you don't know. Also because LSST, you don't know what kind of data products you're going to get. You don't know what kind of pipelines they'll be using for their science. So right now we are going to be part of the, oh my God, it's raining. We're going to be part of the LSST Galaxy Science collaboration so that we can sort of have a say in how the pipelines are set up right at the get-go, like right now.
Okay, okay.
Okay.
Nice.
If there are any other questions and you're feeling shy, please feel free to drop me an email. I'll send my ID on the chat.
For collecting the data, which sky survey are you using?
1 second. So right now we are using the hypersupreme cam of Subaru. The survey that I am drawing from right now is called PDR wide. So it's basically a wide survey between I think declinations of minus no minus 10 and 10 and then 40 and 50. So if you look at PDR2 wide, you can see what survey it's from in the hypersuprime cam of Subaru. How is the PhD life compared to BSM? Oh, there is another question. Using supernova candle. Oh, okay. You already asked this. Okay. Sorry. How is the PhD life as compared to BSMS? I don't know how to answer this question. It's pretty much the same. There's just like a lot more independence, I guess. Like people just assume I'm an adult rather than just not trust that I'm an adult, I guess. Work wise, I think it depends on what advisor you have. My advisors are very, very involved. So I discuss with them twice a day, thrice a day. Sometimes I'm just sitting with them all day and discussing. But yeah, I don't know how to answer that, man. Can you ask me something more specific?
Uh, how is living abroad when compared to living in India?
I mean, it's a first world country, so like, it's very, very different from what we're used to. But I think I'm a lot more independent. I do a lot of things on my own that were usually done for me in IISER, like food, for example, and just figuring things out. Like here, I live in my own house. I have two flatmates. I do my groceries once a week, once in 2 weeks. A lot has changed because of the lockdown. So things are very different from what they would have typically been like. Other than that, yeah, you worry less about things, I think, because a lot of things are typically easier to access. Uh, Socializing is pretty much the same for me because I talk a lot. Other than that, work-wise, there is no difference. I have had pretty much the same experience both in Ayuka and here. Very, very supportive advisors, very supportive postdocs, supportive grad students. I have a very, very nice group here, which I think I'm very lucky in that way. Yeah, that's about it. How is the social life? How do you spend your free time? How do I spend my free time? So we were in lockdown for like for a greater part of this year. So free time was just talking to people, cooking. I traveled a bit during the summer, which yeah, I went to the south of Italy. Other than that, what do I do? I haven't had the time to cultivate any hobbies as such because everything was shut. Um, I watch movies. I go out with friends a lot. Not anymore. We stay home. We cook. Right now, I'm running for student representative in the academic senate, so that is taking up a lot of my time. In fact, that's what I was doing this morning. So that's how I'm spending my free time. I spend a lot of my free time with my group actually. Just socially, we go out a lot, we discuss a lot, and so my institute also has coursework for a year, so that took up a significant part of my time. I was doing classes, I was preparing for exams, and the way the exams are done in Italy are very different in that you have you take a date with the professor and you show up there and you're just asked to present on the blackboard. So that was very, very stressful. So it took up a lot of my time to just mentally prepare for that kind of exam. And also, a lot of the professors allowed us to do semi-research ideas for the exams. So we were allowed to pick topics that are research topics and then study them, and then either make a proposal or do a short bit of analysis. So yeah, that took up most of my time up until now. And right now so I have one advisor in this city, and my other advisor lives in a city which is slightly like 1 hour away. So I travel back and forth quite a bit. So that eats up a lot of my life. Do you need to know Italian to have a social life, or even in general a daily life? It depends. My school is very international. Also, my Italian friends are very, very, how do I say, not traditional in this way that they like to socialize with other people. They're not very engaged in just themselves. So they have made a huge effort to include me. But that said, I find it very helpful to know a bit of Italian, and I'm learning. So I really enjoy that. But as such, you don't need it. You can get by. It's a bit difficult in the beginning because you have a lot of bureaucracy to handle. You have to get like a permit of stay. Also, Sujay knows he's living in France. But other than that, yeah, I mean, you can get by in a social life really with just English. You'll always find people who want to get to know you and also want to practice their English with you, because Italians are somewhat insecure about the fact that they don't know as good English, which is not true, but sometimes they also, yeah, but knowing Italian is a definite advantage. No, I'm not going to speak some Italian. I'm sorry.
I've always wanted to ask this: how's the Italian food? Like expectation versus reality.
Okay, it's nothing like what we eat in India. It's very different. It does not have Indian spices in it. There is no white sauce. Italians hate the concept of the cream in white sauce. I would say it's much more varied. Like there's a lot more variation in the cuisine than we see. There's a lot more seafood than we see in India. I enjoy eating all kinds of food. So for me, it was a discovery, but it was still very interesting. It was great. My flatmates cook very well. So they make a lot of interesting things. In the restaurant, okay, I still sometimes miss the kind of spicy food that we have. So I have Indian friends and we get together and cook. But Italian food is great. I mean, compared to all the other kinds of European food, I think Italian food is really, really great. I think the fact that daily food is along the lines of pizza and pasta makes them healthier than Indian Italian pizza. Yeah, I think so. Because the food is actually really healthy and balanced, even in the canteen. Like they always have some carbohydrates, they'll have some protein, some salads, some fruits. So it's all very balanced. And if you, for example, sometimes I eat at home, and when my roommate cooks, it's very, very healthy, but still very tasty. One other thing that I see is that the ingredients are very fresh here, and you really have very high quality controls on what kind of stuff that people can sell in supermarkets, including the fresh produce. So, you know,
A while ago, you actually mentioned pipelines, correct? With respect to sky surveys and etc. What does that really mean, and what does it entail?
pipelines are basically any set of programs that you use on any raw data to give a set of final products. So you could have a data processing pipeline that takes your raw images from whatever telescope you have and gives you clean images and spectra. It could be a program that takes your clean images and spectra and gives you the value of a very specific parameter that you want to measure in those. It could be anything. So basically, it's like a pipeline. You put in certain product and you get certain product in the end.
Yeah.
Except
Okay.
it modifies
Yeah.
the product a bit. Yeah,
Yeah.
that's it.
Thanks.
Hello.
Hi.
Hi. So you extended your BSMS project, right?
I didn't. I took my 10th semester off, so I took some time off. So I dropped the 10th semester, and then from January to, July, I think, yeah, I had a break. And then I resumed in August.
So then when did you apply for PhD?
That's a good question. I applied, so I graduated in December of 2018. I applied in July of 2019, and I started in November of 2019.
So it was like your fifth year effectively lasted for like 1.5 years, and then after that, one more year before you started your PhD.
Um,
Almost.
Nearly. Almost, yes, almost.
And then, like, do you feel any repercussions of there being that 1 year gap before your
No,
PhD? Because I've
not
heard a
really.
lot of people saying that they lose momentum and so on, and
No.
then they find it hard to come back and all. So I just
I
wanted
mean,
to ask.
if if you're doing something and you're relying a lot on momentum to get things done, dropping it halfway means that it's difficult to come back to it. But I mean, as such, research is not a race, right? You can also, okay, if you take a specific project and you lose momentum in it, it's difficult to come back to it. But on the whole, I think it depends what you make of it. I think I was very lucky in that my recovery was very fast. Typically takes much longer, and I was able to resume work at a reduced but decent pace.
Hmm. More
It
so
really depends.
because more
But
so
I
because
should say that there is no difference. There is really no difference at this point. I feel no different than if I had started in 2018, for example.
okay. More so because you're doing a 3 year PhD, so it must be
I'm doing
like
a
a
4 year
lot more.
PhD.
Oh, okay. So, like in the US, there are courses to do before you start your research, and
I also did
like
some courses. So
okay,
it really depends. You have to find a school that fits your requirements well.
huh, okay,
That's all.
Well, I'll add one thing here. Like taking a year off really doesn't have any impact on the PhD in here. Like no one gives a damn about what did you do. They just gives that whether your research is okay and you want to do it or not. So
Exactly.
this race of like this fear we have, like, oh, if we lose 1 year or something, I will not get admitted for something. I don't think so. It's not at all true. I mean, here they don't really care, and if you show them that you're good in the interviews and all, it doesn't have really impact on your admissions, for example.
Yeah, completely.
yeah. I was more concerned about how they would judge our ability to do research and so on. Like,
For example, okay, here is what I think. I don't know if Sujay would agree. Is that if a school is judging you based on the fact that you had to take time off for your health, do you really want to be in such a school? This is what I think.
Yeah, I agree. I agree. But I mean, yeah, but no one asked me anything. Also, like no one asks you what you do. They just see your grades and they just see your research application and your interview, and they will probably not care before applying what you did for here. Like I
Yeah.
have some PhD students here who have taken 2 years job or just was not doing something, and then still they are doing PhD. They are even 26, 27, 28 when they started the PhD.
Yeah.
So it's absolutely they don't judge at all.
Yeah, I
To be
think the
honest.
best person in my PhD program, she started her PhD this year with me, and she was last year with me, and she was 26 when she started. So it really does not matter. Is
okay, thanks.
Python the most common language for astronomers? I'm sorry, I cut you off, Shreya. Is there anything else you wanted to ask?
No, 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 no. Thanks.
Okay,
Thanks a lot.
no problem. Is Python the most common language for astronomers? Sujay, what do you think?
Yeah, currently yes. At least for next 5, 10 years, 5, 6 years, I think so. Maybe Julia is catching up, I think, but
Really?
yeah, probably for data analysis, Python. Yeah.
A lot of people are using Python. A lot of people refuse to transition from Fortran or C, but I think most people are using Python. I mean, at least trying to.
So, is there any point in learning Fortran or C if you're not very familiar with it and you are familiar with Python?
If you can use Python effectively, why not? Go ahead. Uh, I started programming with a very different language. So I've made a lot of language switches over the years. It helps to program in a language which does not have modules for you to do everything, so you understand how it works. But it's not fundamental. I mean, you can learn to use modules without knowing how they work if it helps. But yeah, sometimes it helps you debug to know Fortran and C because it really breaks down the code that you need to write. But I mean, you can also learn to do that in Python in universe. Instrumentation and astronomy seems to do mainly with engineering since you did a project written. A lot of people do go into instrumentation from science. A lot of people also from engineering go into it. There is no one way of doing things. If you're interested, you should work on it. You should learn electronics, whatever instrumentation you're doing. You should learn optics if you're working with mirrors. And it's just what you make of it. You have to build on your skills and you have to keep working at it. You might have, okay, engineering students may have a certain advantage over you, but you could also have a certain advantage over engineering students. So it cancels out. It really does not matter what you do in that
Yeah,
in
yeah.
that way.
So like that's what I wanted to know. Like what are those things which science students can bring to instrumentation, which like uh,
Your understanding
give
of the
them an
science
edge.
case. Your understanding of the science case. So you're
Okay.
doing instrumentation for a certain science goal, and your understanding of that is what is going to give you an edge. Which doesn't mean that an engineering student does not have that understanding. They can. You just have to sharpen the edge that you have, and then that's what you have to build on. But yeah, there is really no. For example, if you go to Pawan's lab, there are engineers and there are people who have done BSc, MSc, and they all do equally well, I think.
Okay. Thanks.
No, I chose to explain on my SOP why I took time off, but I don't even think anybody noticed because really in Europe nobody cares. I don't know about the US, but nobody asks you even. Nobody cares why you took time off. And people do it all the time. You take a semester off for certain reasons, you come back, nobody cares.
Okay, Okay, so we have reached the hour mark now, and if anybody has a question, please put it forward. If not, then I'll stop the recording. And I encourage you all to stay behind and chat with the alumni present here and Nandini. And if Nandini you have like time, uh,
Absolutely.
so if nobody has a question, then I'll stop the recording now, and you all feel free to hang back and chat.
Also, you can send me an email if you have any questions.